Record. Okay. Oh, what is that? Oh,
That's the minus.
the minus. Is this on minus? Wonderful. Okay. What?
Yeah.
Am I getting the mouse down?
The what?
The mouse.
You want to get it back?
Here we go. Wait,
It's system. What are you trying to do?
trying to get it back here. Okay.
What if you just don't present in slideshow mode? Or are there innovations thing?
Yeah, we can do that.
Okay.
You want to do that?
Sorry. Okay. How do you exit this? Oh. Okay, we can just present. Does it look better?
Why is it? It's like chopping off part of
If
your
you just
slide.
click present or slideshow again.
No, I got it. So, yeah, a loading. Are you recording? Now it's just.
Why?
Oh, okay. I think it's a projection.
If I move, it doesn't move. Oh, that's not very good.
What if we just
Have the like separate, it's just like one on the screen and one on the. So like,
Okay, we can try.
we
that.
can just like project. Yeah, I can screen share the slides separately.
Okay.
Alright.
Yeah, yes, I'm trying to get my mouse. Oh, that's awkward.
Nice.
That's awkward. Where did my mouse go? Oh, there it is. Okay. That is so awkward. What? That is so. Okay. Probably.
Does it like, no.
Alright. Oh.
Over there, there's no.
There's no what?
There's no slides here.
Wait, we can just like go to the next one. Because you can't control this.
Yeah, okay.
Yeah, just like say when you want to go.
And it's recording here.
This.
Yeah.
Oh, it should say, yeah, it is, it is.
All right, this is going to be the first part of the final review session for 61A. Next slide. All right, a quick disclaimer, this is an unofficial review session and CSM is not affiliated with the course. Yeah, quick disclaimer. All right, and the topics we're going to cover today, these are the topics we're going to cover for the first part of the review session. So the first hour will be functions, recursion, and lists, container environment diagrams. And the second hour will be from iterators and generators to linked lists. The second part of the review session will cover scheme and SQL, and that'll be Saturday, 5 to 7.
That'll be the walk.
All right, functions and higher order functions. Defining a function, there are two ways to define a function. The first way is the way that's more common, I guess. Def name and the parameters, and then a return statement inside. So that's the first way. And the second way is to define a function with a lambda expression. So these are both doing the same thing, but in different ways. And every time we call a function, a new frame is created. So the parent frame is where the function is defined, and looking up names, we look it up in the current frame, and if not found, we go to the parent until the global. Higher order functions. Higher order functions are functions with inputs or outputs as other functions. So the return values are defined locally, and the call expression can be used as an operator. So for example, if you see over there, make adder 1, 2, there are two different arguments there. So make adder 1 will return a function that takes in 2. Okay, this is the first question. I'll explain it briefly and then you guys can try it out. So the first thing it does is it takes in a positive integer and then returns a function. And then that function takes in a positive integer b and prints the sum of all the natural numbers from 1 to a times b. Is there the paper that this question is on?
These are just the ones.
Got it. Okay, try this question now. I'll give you guys like 3 minutes.
We're working groups too. Do you want to talk about that? Business side?
All right, in the interest of time, I'm gonna go over this question with everyone. Okay. Ashley, could you? Go until slide 17, when all the blanks are filled out. Okay, so the first thing to note about this function is that when it's called, it takes in an integer a and then returns a helper function. So the first, probably the easiest line to do is the bottom line, return helper. And then after you return the helper, that helper function itself, it takes in another integer and prints all the sum from 1 to a times b. So that's what this does. Lines that you can change, I total equals 0, 0. That can also be 1, 0. Yeah, any questions on this question? Yeah.
Why do we consider I the y?
Because keep in mind that we're doing the sum from 1 to a times b, right? And so I, in this case, would act as that counter to keep track of when we reach a times b, which is what the condition is. Yeah.
Turning the print sum on a plus b part, what is that?
Yeah, because in the question, I think like in the earlier slide, when we want to call this function again, it'll return the sum of 1 to a plus b times c. And so in this case, a is being replaced with a plus b, and it'll take in another integer c. Okay, cool. There's another question as well. Yeah, there's a bunch of subparts, so we'll spend like 2-3 minutes on each one. For some tips on this question, if we look at the test case, fun squared triple 5, fun squared triple should return a function that takes in 1 input. So keep that in mind when you're going through each one. Yeah, if we look at the test case, fun squared triple 5, fun squared triple should return a function that takes in 1 input. So go through each one and make sure that they return 1 input and that they, for example, for these ones, take in 1 input. All right, let's go over the question. All right, so just going through each of the options, part A, Notice that f wouldn't work because f itself takes in an integer and f is a function, so that one wouldn't work. For B, return lambda, there's no argument for lambda, so if we return this, the bracket 5 wouldn't work, so not B. Part C, fun square takes in 2 inputs, and in here it only takes in 1, so part C also wouldn't work. Option D, that one would work because it takes in 1 argument and yeah. Part E, same reason as part C, takes in 2 inputs, so that wouldn't work, and part F would work. Any of those confusing? Or need clarification? Cool. Let's go on to the next part. I'll just go through this one. So for the quadruple is equal to fun square and there's a blank, right? And we want to basically quadruple the input that we get. Note that fun square repeats the function twice. And so the function that we make has to do has to double the input. And so the answer that we should get is lambda x 2 times x. For the next subpart, I'll also just go through this one. So note that this one takes in triple and does it 4 times. Fun square, was it fun square? Yeah, fun square before only does the function twice. And so fun fourth, we have to do fun square and fun square again, so that we do triple 4 times. So the answer you get should be that. Okay. I quickly ran through all those. Any questions on part A, part B, or part C? This one again? Absolutely, yeah. So note that fun fourth triple 10 should take in triple and do triple 4 times onto 10. So if fun fourth was only fun square, that would do 10 times 3 times 3 only. In this case, we want to do 10 times 3 times 3 times 3 times 3. And so what this does is it does the function 4 times. Yeah. Right. Both of them require a 1 argument input, right? So this one, lambda x, that's a 1 argument input with x being the input. And fun square, that also, note that fun square returns a function that takes in 1 input. So this would also just take in 1. Yeah. Yeah. They're different because I mean, they're technically not different. They both take in 1 input. Lambda x is an undefined function, right? We want to double something, so we have to define that ourselves, whereas fun square is a defined function that returns a function. So they're both essentially.
You do this because it said you can't use the lambda expression.
That too.
Got it.
Yeah. Okay. Cool. Okay, that pretty much covers higher order functions. We're going to move on to recursion now. So the idea of recursion is to solve a problem by continuously dividing that problem. So this one right here is regular recursion, working down and then going back up. And then over there, that's tree recursion. So it calls on itself more than once in a body. There's 2 parts of recursion mainly, the base cases and the recursively buffet. So the base cases handle when you stop recursion, and the recursively buffet is how you handle going down the tree or path. Okay. Quick question there. There's also the paper and the question if you want to pull it up yourself. You should draw it out and like if the input depends on one or more function calls. So Fibonacci, for example, it depends on the past too, right? So that would be true divergent. Factorial only one, so that would be general. Also, because we're gonna go slightly faster, it might be easier to like work with the person closest to you. Also, I'll see you. Okay, all right, let's go over it together. So the first thing we should do when approaching these types of questions is to split them up into the base case and the recursive leap of faith. So in this case, these first two lines are going to be the base case, and everything past that is going to be the recursive leap of faith. In this case, this would be tree recursion because we're doing with first and without first, which are the two scenarios that are possible here. Either including the first number or not including the first number. All right, so the first part A, if the list is empty, we return just an empty list, which, yeah, right there. Okay, and for part B and part C, if we include the first number, we're going to run recursion on everything past the second one. And if we don't include the first one, we'll do that. Any questions on these two lines? Yeah.
Why did they pass the second one according to?
Right, good question. By the way, the question asked was why everything past the second one? Because if we include the first one, we're skipping the second element and going to the third one, right? And so in this case, that would be in list 2 and after.
How do you get the first element?
Right, and that's what this line is going to do. Okay, and so the first line, the condition was that it's in strictly increasing order. And so the way we would write that is okay, so we include it if that condition.
What is a list? of elements?
Sorry.
Why the first part is a list?
Because the return value we get is going to be a list within a list. Like, what we're going to return is a list of lists. Yeah.
What about list first?
Mhm.
Why is it really a list slide from the second, the third element?
Yeah, the question asked was why is it the third element onwards? It's because if we include the first element, we're skipping the second element. And so everything past the third, we can run recursion. That makes sense. Good, yeah. So like we have two choices, right? To either include the first element or not include the first element. If we include the first element, we can run recursion on the rest and handle the actual like current list here. That makes sense. Okay. We'll just go on to the next question, just for time's sake. All right, this one's a pretty typical question. We're given a total and a list, and if that list can sum up to the total, we return true, else false.
Also, if you have any questions that were not answered, we'll be monitoring the Iterate as well. If you have any follow-ups later today or something, report to us.
Okay, if you want general hints for this question, do you guys think this is recursion or tree recursion? Tree recursion, and why do you guys think it's tree recursion? Because in this case, right, if we're given a list like that, for the first example, we can either include two or not include two. And so those are two different scenarios, right? And those two scenarios encompass pretty much all the scenarios that are possible. And so when your return statement right here, try to make this reflect including two and not including two. So if we include two, what's the subproblem that we're asking? Well, we're asking if we can make 8 from the remaining list. That makes sense. Okay. Does anyone have any questions about anything? So all right, cool. Let's go over this as a group. Okay, so part A covers the base cases and part B, C, D, and E cover the recursive leap of faith. Does anyone have any ideas of when we return false? So what goes in part A? And less than 0, absolutely. And what's the other case? You know, guys? Okay, so the other case is if coins, the list is empty. And so the way we write that is there. Okay. And for the recursive leap of faith, okay, part B is there. We can either include, this is not including the coin. So we're just doing n coin. And then what's the other one? It's going to be if we include the first coin. So change n minus coin, and then the rest of the list. The reason why we use list coins is because we want to make a deep copy of the list. Because if we do both of these and we execute this first, this will manipulate the list in there. So these are two separate lists with these same elements. Okay. And if either of these are true, we return true. And so the command word in C is going to be or. Okay. Yeah.
So does that mean like the reason why we use the second coins as the list coin is because we want to off this line?
The reason why we're using that is because when we execute this list is separate from that list, right? And so we want to make sure that those are separate pointers to separate lists.
So we kind of make a copy.
Yeah, we kind of make a deep copy of it.
Yeah.
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 This one right here? Yeah, absolutely. So the two possible scenarios are including the first coin and not including the first coin, right? And so the first part B right here, this is the scenario where we don't include the first coin. So it's change n coins. And the second scenario is when we do use the first coin, which is n minus coin and the remaining. And if either of those are true, we return true, and so it's 4. Yeah.
Why do we use list of coins?
Yeah, why do we use list of coins? Because we want to make sure that these two lists point to separate lists. When we execute this, we're going to tamper with that list, right? And we don't want that tampered list to be in there.
Two different.
Yeah, two different lists, essentially.
Why not list of last?
You could, if you do coins, bracket colon, that would do the same thing. Valid. All right, I think there's one more question. It's pretty. To the question in the chat, you wouldn't because you pop it in the line above. And so there are two separate ones. All right, let's go over this question. There's only two parts of it, so I'll just ask whether you guys have any ideas on this one. Does anyone have any answers for part A? Yes. Absolutely. T-dot branches, zero dot label, because there's only one branch. So T-dot branch is zero, but yeah. Right. And on the else statement, does anyone have any answers for part B? Mhm. Absolutely, yeah. You're running recursion on the branches to find the fruits. Valid. Any questions on that one? Yeah.
Again, branches. Or so that you look at each individual branch instead of the whole.
Right, because the way we define a fruit is there's only one child, right? And so in that means that there's only one branch. And so that's why we need to do T dot branch is 0.
Yeah, and so the second part.
Yeah.
That's for being T dot branches, that's like checking each of the. branches.
Check each individual branch to see if there's a fruit on that branch. Okay. Valid. Okay. All right, the last topic I'll cover is list environment diagram. We'll kind of go quickly on this one, but there should be 2 questions. Yeah.
I from the last one on the sum statement, and I was looking at like this would kind of ask. I had some, and then it was comprehension B for B in T dot branches if like the sum through tables stuff.
That might work. That might work. Wait. I think that would work. Yeah. Listening to it. That would work. Okay. Okay. I'm gonna skip all of this. I'll go over the important things though. Whenever you call a function, make a new frame. And when you evaluate the operands and then the operator. How far are we on the diagram? All right, let's go over this question. So I'll go over each line and then the resulting diagram, you can check with your own. Okay, so we start by defining both of these and we don't run the bodies. So we'll have 2 pointers, funny and sad. Okay, and on this line, line 9, we're gonna swap them around. So the pointers are gonna go to the other one. Okay. All right, everyone good so far? Okay, for line 10, we're gonna evaluate the operands first. So that's sad 1. Sad in this case points to funny. So we're gonna go through this body of code. Joke in this case is 1, so hoax is 2, and we're gonna return funny 2. And so we run here, joke is 2, so hoax is 1, and then we return 2. Okay, which brings us back here to funny 2, and then we open another frame for sad. With joke is 2, and then hoax is 1, return 2, and then we make results 2 in the global frame. Okay. Any questions on that or any part of that? That you know? Yeah.
So we have a function inside how we don't always do it inside a phrase that is said first.
Yeah, the question was whether you do the inside function first. Yeah, you do the inside one first because that's the you evaluate the operand and then the operator. So the operand would be sad 1, and then we work out sad. Cool. The next question is also a parameter question.
Okay, where it only functions.
We have one question. Yeah. This is our last question for my half. Do we want to go over it together or just you guys try it and then I'll go over it. All right, let's do both. If you want to do it together, if you want to do it individually, Rita. Okay.
It's part of mine, so. Yeah. It's not.
All right, to make time for the other topics, I'm gonna go over this question now. Wherever you are, you can check where you are and then just follow along. Okay, to start, we're gonna define cold in the global frame, and then define rain, and then the day. So the first three lines are up until line 9 should be pretty straightforward. And then for line 10, we're gonna evaluate the operands and then the operator. Cool. So steps are. Okay, so we evaluate day 0 first. So we evaluate day 0 and then we're gonna go into cold. We pop the list and then we return night, which is defined here. And this should be a result. Sorry, I had to blitz through that because there's not a time for a second, but this should be. Okay. Right, do you have any questions on the first half? So functions, recursion, and list. All right, we're gonna take like a 2-minute, 3-minute break and then go over these things.
Thank you. Yes.
Sorry.
It's fine.
It's a lot of concepts.
It's just like, yeah, it's more. I just looked through it. So. Thank you.
I did. Oh, this man. Oh, this is something.
Yeah. Okay, so our next section is iterators and generators. I think you skipped one. So. All right, so first a small review of iterators. So iterators iterate over iterables, and an iterable is any container that can be processed sequentially. So that would be things like lists or strings. Iterators hold pointers of the current index of the iterable they are on. So if you have an iterable like a line of people, the arrow that points to whoever the person is that's in the front of the line is your iterator's pointer. Next one. Okay, then we have generators. Generators are like a specialized kind of iterator. And it's like a function that where the body contains one or more yield statements instead of return statements. Generator functions return generator objects, and we call these objects to yield values with next. It's the same way that you find the next item in an iterator. So first we evaluate the body of the function until we reach a yield statement. And then second, yield pauses the function and yields the value. And the local state is saved, so we can resume evaluation where we left off when we call next again. A stop iteration error is raised if we call next on an object that can't yield anymore. This applies to both iterators and generators. Okay, so generators, yield versus yield from. Yield returns one element, and so one example of this is for I in range 5, yield I. And yield from repeatedly returns values from an iterable until it can't yield anymore. So yield from range 5. Both of these do the exact same thing, just in a different way. Okay, next we have our first question. I think we skipped this one, maybe. Do the next one. Midterm 2. Fall 2019. Yeah, okay. So short explanation of this question is kind of like count partitions. Basically you're yielding strings that describe all partitions of n using of parts up to size m. Each partition is a sum of non-increasing positive integers less than or equal to m that totals n. Partitions function yields a string for each partition exactly once. So if you remember count partitions, it's similar-ish, except it's a generator function. So I'll give you guys a few minutes to do this. Okay, I think we can start going over this question now. Ashley, can you? Ashley. So our first two lines here are going to be the first case. If you look through the doc test, you'll see that the very first partition that we are yielding is the one that is using m, I guess, if they're the same. So our very first case is if n is m, then we yield the string of m. Then, because this is a generator function, we continue down for the next ones. So if n is greater than 0 and m is greater than 0, we're looking through all of the partitions where we use m as one of the subpartitions. So for p in partitions of n minus m, we yield string of m and then plus the plus sign and p. So that's like how we end up with this like format. And then the very last step is when we don't use m as part of our partitions, we use 1 less than m. So we yield from partitions of n and m minus 1. Any questions on that? Okay. Now we can move on to the next question. The next question, implement a generator function all links, which takes in nums, which is a list of lists. And basically you're creating a bunch of linked lists that from the list of lists. So the first item of the linked list can be the first item of any of the lists. And the second item would be the second item of any of the lists within the list, and so on and so forth. And here's the skeleton code. I'll give you guys a few minutes to do this one as well. Okay, I think we can start going over this question. So, very beginning, we have an if statement, and this is going to be our base case. We're checking if our lists within the list are all empty or not. If they are, what we do is we yield link.empty because there's nothing that we can do with empty lists. No linked lists to generate. In our else statement, we take all of the rests of each list, so not including the very first element of each of the smaller lists within the larger lists. And we do this by slicing one slice x for x in nums. And then lastly, for first in x of 0 for x in nums, which is all of the very first numbers, we create our linked lists. So for our linked list that we've created with all of the rests, so for item in all links of rests, then we're yielding link of first and then item. So we're taking all of the smaller linked lists and then tacking on to the front all of the possible first numbers. Any questions about this?
Why I use yield as return?
Yeah, so this is a generator function. So it says implement a generator function, all links, which is why we're using yield instead of return.
Return.
No, because generator functions, we have to use yield. So a generator function returns a generator, and to do that, we have to use yield instead of return. Any other questions? Okay, if not, we will move on to object-oriented programming. So there are a few essential elements of object-oriented programming. So it focuses on distinguishing objects using two aspects. So there's one thing, their characteristics, which are class variables and instance variables. So class variables apply to all instances of the object, but they can be overridden. So for example, if you have a car class, then having 4 wheels would be something that is like a class variable, but it can be overridden. Not all cars have 4 wheels. And then instant variables only apply when the object has been instantiated. So this could be like the color of the body of the car. So what they do are the methods, and we have instance methods and versus class methods. Similar idea here. Okay. So class variables and methods apply to the abstract concept of the instance and possibly to the actual instance itself. So if you don't instantiate the dog class, it's generally known that a dog can bark. But when you have an initial impression of an object, those characteristics can usually be written as class variables. And then instance methods and variables only apply to individual instances of an object. So these ones can only apply after instantiation has happened. And then next we have inheritance and overriding. So you can create subclasses of a parent class. So creating like a Chihuahua, which is a subclass of dog. And in order to use like the inheritance part of it, you have to use super. What if you want the child class to be different in some way? That's possible. You can override methods in the child class by redefining them. And you always call the redefined method variable for the child instead of the parents. Okay, can skip this one. And move on to string and repr. So string and repr both return Python expressions. There are 2 different intents like for usage. Repr is not meant for the client, it's meant to return an accurate representation of a Python object for a programmer. And then string is supposed to be displayed to the client. So a string of an object calls object.stir, and then repr of object calls object.repr respectively, and then printing object calls stir, but putting it in the interpreter will call repr. All right, then next we have a problem. So in this problem, we have this larger class called learnable content. It's a base class that is just all types of learnable content. So the very first part of the problem, we're creating a class called exercise that inherits from learnable content. Can you go to the next slide? Yeah, and the thing that is different about exercise, if you can see in the doc test, is that it has something called num questions, which is not within learnable content. So we're just creating the initializer for exercise. I'll give you like 1 minute to think about this. How you would write the initializer. Okay, so like I stated earlier, when we have inheritance, we want to be using super. So you go to the next slide. Our very first line is going to be super.init of title author. So this is calling the initializer of learnable content, so that we can initialize the title and the author. And then next we have self.num questions equals num questions, where we're creating the instance variable number of questions, and setting it to be whatever is passed in. So in the dog test, for example, num questions becomes 5. Okay, and then the next part of this question, we're creating another subclass called video. So if you read through the dog tests, you'll see that video has a few things that are different than learnable content. One of them being there's something called license, and another being there's something called num seconds, and there's a stir method. And there's 3 things to write here. I'll give you like 2 minutes to do this one, to think about it. Okay, so when we look at the doc test, we see when we call license, or when we are accessing license from video, we're using capital video, which should indicate to us that this is a class variable and not an instance variable, because we're using the name of the class instead of the name of instance, which is vid. So can you go to the next slide, please? Our very first blank is license equals this string, which is what's in the doc test. So we know that license is a class variable. Next we have the initializer. Again, we're using super to initialize through like the learnable content initializer for title and author. And then the next line, we're creating an instance variable num seconds that just assigns number of seconds to what is passed into our video initializer. And then last but not least, we have our string. So when we call string on video, it returns the title by the author and then the number of seconds. So in this case, we use the super string method. If you look back in the learnable content class, there's string that is an F string of self-title by self-author. So we just used that and then tacked on the number of seconds in parentheses. Any questions on this? Num seconds wasn't in learnable content.
Oh, okay.
Yeah, so num seconds is like a instance variable of specifically video and not learnable content. Yes.
For the last one, it's you have returned super the 2 parentheses dot string and then the 2 parentheses. So is it because it doesn't like take in anything specifically the last 2 parentheses?
The last 2 parentheses. Oh, string and then yeah. So it's a string method, right? So you have to have the parentheses to say that it's like a method call. But yeah, string of learnable content doesn't take in values. In the string one. Yeah, so you can't really see the learnable content class in this specific slide, but learnable content has a method called string, it has a stir method that returns the title of the learnable content by the author. So we're just using the super, which is the title by author, and then to change it into what we want in the doc tests, we're just tacking on at the end the number of seconds of the video. That makes sense. Any other questions? Okay. I think in the interest of time, we might want to move past the next object-oriented programming one. So any like remaining questions on object-oriented programming before we move on to the next section? Okay. If not, our next section is trees. So a quick overview of the tree class. We have the code of the tree up here. So trees have a label and then they have branches. So trees are recursively defined. A tree has a list of branches and each branch itself is a tree. This means that leaves are also trees. And information in trees are stored in the labels of each node. So the next slide shows us a representation of a tree, I guess, more visual representation. So a branch is a subtree of a tree, which is a tree itself. A root is our very first node. There's a label, and then there's a leaf. A leaf is a tree itself as well. It just has no branches. Okay, and then we have some tips for tree traversal. These are not always the case, but like sometimes or very often it is the case. Our base case may involve tree or t.isLeaf, but sometimes it might not require it. If we're iterating through the branches, there are no branches to iterate through, and that itself would be our base case. Second, we iterate through each branch. We do this a lot with list comprehension, specifically because branches are contained within a list. So for example, has B for B and T dot branches. And then recurse, often easier to focus on one depth at a time. It's just like a tip. And then iteration is only necessary in specific cases. And then 4, you walk through your solution with a simple or a complex test case. Often it's easy to look at the doc tests and draw it out and see how it works before you start coding. That often helps me. Okay, next we have a question called spring pruning. You can go to the next slide. Oh, actually, okay. So we're filling in the function so that we delete all nodes whose label is strictly less than that of their parent. So if their parent is at even depth, so not all, but only at depth where there's even. Or whose label is strictly greater than that of their parent if their parent is at odd depth. So it's a little complicated, but essentially like every other node we want to be less than their parent, and the opposite, every other node we want to be greater than their parent. Okay, so the next slide is our skeleton code. Yeah, and hopefully you can see like an example of the pruning on the top. The left side is like your initial tree, and then the right side is your pruned tree. Yeah, I'll give you a few minutes to do this. Okay, we're gonna go over this question now. So, if you see here, there's a helper function with this one in this function called prune level. It keeps track of a variable called d, which is our depth. At the very bottom, you can see that our depth starts at 0. So we have two cases here, right? If the depth is even or if the depth is odd. Because remember, we're trying to make it greater than or less than depending on whether the depth is even or not. Very first case, we have depth is even. So if our depth is even, we want our branches to keep our branches if the branch label is greater than the tree label. And then if it is odd, if it's less than. Go to the next slide. So we do this with our list comprehensions. So we're keeping B if B dot label is greater than or equal to T dot label, and then B if B dot label is less than or equal to T dot. And then the last part of this is our recursive call. So for B and T dot branches, we want to prune the next level down, and we also want to increment depth as well by 1 when we do this. Any questions on this problem? Yeah. What do you mean by how does it get B?
Like, how do you know? Oh, because when at the end of the holiday, we start at 0.
Yeah, so the root node is 0, depth 0. And then we increase by 1 for each level. That makes sense. Okay. Any other questions?
Just summarize the logic.
Yeah, so essentially we start with a tree. Our very first root node, we check at the root node if each of the branches labels are larger than our root node label. If they are, we keep those branches. Then we move to the ones that we keep and do the same thing except for less than. And then we keep going down until we get to the very end of the tree. That makes sense. Yeah, so that's in our for statement at the bottom. The for B and T dot branches, we're calling prune level on each of the branches. Just with our depth incremented by 1. Yeah, so we're pruning all of the branches of our very first node, and then we prune the branches of all of the ones that we keep, and so on and so forth. Okay. Any other questions? If not, we can skip this next problem. And move to part B of question number 7. So part A of this question you guys did earlier in the tree recursion section. And now we move to part B. So it's hard to see, but part B, we're implementing pruned, which takes a tree instance T. If T contains at least 1 fruit, return a tree instance with only the nodes of T that appear on a path from the root to the fruit. If T contains no fruit, pruned T should return none. Calling pruned T should not modify T. So this is non-destructive. We have to create a new tree. Hopefully you can see the code well enough. If not, try pulling up the slides on your computer. I'll give you a few minutes to do so. There are 3 blanks here. Okay, I think we can go over this problem now. So our very first blank is if rooted branch of T, so if our tree is a fruited branch, what do we want to return? So if rooted branch returns true, then we just want to return true, or return T, sorry. So if you remember from earlier, fruited branch is a function that takes in a tree, and if it only has one child that is a fruit, then it returns true. So this is why we do this.
Is it the same with these branches? In the theorem?
If we say T dot branch instead of T, it's not exactly the same thing. So we're returning the tree itself as well instead of the very first item of the branches. Okay. Then the next part, cut, is a list comprehension of pruned B for B and T dot branches. So cut, we're basically pruning all of the rest of the tree in that part. That is our recursive call. That is not part of our answer though. And the next part is if, and we'd want to do any cut because we're seeing, so true is like if we have our fruit or not. So we want to check if there is any fruit in this tree. And if there is a fruit in the tree, we create a new tree. So part 3, we have our new tree has to contain a label and then all the elements of the cut list that aren't none. So one way we can do this is tree of T dot label for B for B if B, and if B is just a checking to see if B is none or not. So you could also say if B is not none. These two things are the same thing. Any questions on this? I know this is a little confusing.
Because of the T dot label type,
Yes.
and where the branches, where do they? What is
Okay, I think this should be B for B in cut if B. Not B for B if B, sorry. That's a little confusing. But we're looking through all the branches that are in cut. And a lot of them are none, right? Because we've pruned them already. But some of them aren't. So we're just checking if they exist or not, basically. Yeah, B for B and cut if B. Yeah. Sorry about that. Any other questions? Any last questions on trees in general? Okay, we'll move on to our last topic for today then, which is linked lists. So a little review of linked lists. The way we create a linked list 1, 2, 3, we use this constructor called link. Link dot, or if we have a linked list and we use dot first, the value of dot first is what's in the box here, so 1, and then value of rest is a pointer to another linked list, which is the rest of the list. And then the next slide is just like our code for the linked list class. Hopefully you've seen this before. Yeah, so you have your first, which is like the item, kind of like label entry. And then rest, which is the rest of the linked list, which is also a linked list itself. Okay. So we have one practice question for this. Don't know if you can see this really well, but essentially we are taking in a linked list called linked list, and we are inserting a value called value at the very first before. So before is this number or some value that you want to insert value before in the linked list. So you're going through our linked list, looking for before, and then inserting value before the variable before. Sorry, the words are really confusing. But yeah, I'll give you a few minutes to do this problem. Any clarifying questions on this? And it's like just a reminder, this is a non-destructive function, so we're creating a new linked list instead of altering the linked list that was already passed in. Okay, I think we can start going over this question. So our very first if statement is going to be our base case. We're checking here to see if linked list is empty or is linked.empty. So if linked list is linked.empty, we're just returning linked list, which is linked.empty. Because if you have nothing else to go through, then we're not inserting anything, nor yes. Yeah. Yeah, we're creating a new list, so linked list. So if you said like return link.empty, it should be the same thing. Yeah.
Please, that would be current UV.
Correct. Yeah, it should be. Okay. Then our next statement is we're checking to see if the current value that we are on is before or not. If it is, we're returning link of value and then of our linked list. Oh, interesting. And then our last statement is if we're not currently on before, we return a new linked list dot first, and then link insert of linked list dot rest value and then before. Any questions on this problem? Value is passed into the function itself. It's the number that we're putting, or the item that we're putting in before the item before, I guess. Yes,
So that way we can put it in our place, right?
yes. Linked lists are also somewhat inherently recursive data structure, just because you have link dot first, right, and then link dot rest, where link dot rest itself is also another linked list. So you'll be using recursion a lot, but it's also possible to do it iteratively. Okay. Any more questions? Yeah, if not, that's the end of this review session. Only covered everything up until midterm 2. So be sure to stop by on Saturday if you want to learn or relearn or review, I guess, scheme and SQL. That's not here though. That's in the WAS. Yep. Thanks for coming, guys.